Hi, my name is Kraig Wheeler. I'm an associate professor in the Department of Chemistry, one of 15 faculty passionate about quality instruction and engaging students in meaningful research. The research interests of this dedicated group span a variety of areas such as microfluidics, dynamics of biological systems, environmental remediation, surface absorption studies, and supramolecular chemistry. The latter topic is related to chemical systems with function created by the engineered alignment of molecules. My research interests over the last 2 decades have focused on the areas of crystal engineering and supramolecular chemistry. The general principles that govern these science areas center on organizing molecules in a predictable manner, because the property of a material is intimately connected to the alignment of the building blocks, that is, molecules and atoms. Advances in this area continue to make important contributions to the development of functional materials with optical properties, drug discovery, and other materials of technological value. During the first part of my career, student-led research projects have centered on exploring the factors responsible for organizing molecules and materials. While there are many types of materials to investigate, crystalline materials have been a common thread in our research investigations. Crystals offer an important framework in which to study materials. Unlike other solids, crystalline solids are composed of 2-dimensional and 3-dimensional arrays of molecules or atoms, and it's this organizational and periodic property that lends itself for study. Directing an X-ray beam at a crystal produces X-ray diffraction that, when assessed properly, gives a clear picture of the crystalline components and their orientation. This is a hugely powerful tool for making important connections between the property of the material and material structure. One can imagine that if you were interested in developing, let's say, a better magnet, knowing the structure of the material could help suggest ways to adjust the material components to improve that property. Our work in this area initially set out to identify the structural features responsible for molecular alignment in crystals. It's well established that hydrogen bonds provide a cohesive force for assembling molecules in crystals and other materials. And our investigations explored the competitive nature of introducing several types of hydrogen bonds in a single chemical system. This work showcased the complexity of predicting the crystal structures of relatively simple components and hopefully offered some insight to important challenges in crystal engineering. An extension of that work followed and looked beyond the role of hydrogen bonds to molecular alignment by investigating the shapes of molecules and their influence on crystal packing. The materials of interest to us are commonly referred to as quasi-racemates. These compounds consist of 2 chemically different molecules that are similar in shape and size but differ in their 3-dimensional shape. These molecules are more or less mirror images of each other and only break this mirror symmetry by the chemical fragment that is chemically unique. Conceptually, this is similar to left and right hands. If a finger on one hand is fitted with a ring, then the 2 hands remain similar but are not exactly identical. By investigating the crystal structure of compounds with the same chemical trait, new insight to material design is possible. Current student-led research projects in my laboratory exploit the properties of hydrogen bonds and molecular shape to drive chemical reactions in crystals. Because these molecules are fixed in space, the chemical process tends to have enhanced selectivity. The particular reaction we are investigating mimics that commonly identified in skin cancers by overexposure to sun's rays. By varying the components of these chemical systems, we can engineer the distance and thus reactivity between the reacting centers. This gives an important opportunity to explore the structural requirements needed to conduct these reactions and in turn shed some light on the fundamental aspects related to DNA photodamage processes that are often the origin of many skin cancers. If you should have further questions regarding this research, please feel free to contact me.